So yesterday I had a problem with the video uploading because of a song that I put, and that's why I ended up not coming back. And then I did this stuff off stream here, and I had to redo some things, put these hacks here because I was having a problem on the data frame, and I had to do two separate ones because I couldn't think of a way to put the transactions in the same data frame of the block information. And I think the way that I did this, it's better now, where I'm putting the transactions on one data frame and the block information on another data frame. And I hit the maximum amount of requests for Infura, and now I'm using the Alchemy. And the problem I was having before was not with the method itself, was with the way that I set up the .env files. So I changed to this way that I saw on Stack Overflow question using os get env, and now it seems to be working completely fine. And I think I'm gonna do this method for now, but the problem is that I saw on the if hash thing, and it seems like there is up to this date around 14 million blocks in the Ethereum blockchain. And from Infura, I have 100,000 requests a day that I can do with the free one. From Alchemy, I haven't tested it yet, and I didn't understand the site, what the limit, what they're saying the limit is. There's something about computing which is around 300 million, but I don't think that's the case. It's probably around 100,000 if I had to guess, because it just makes sense. So if you do 14 divided by 100,000, it's gonna give you 140 days. Let's see. Let's make sure. Yeah, 140 days. This means that it's gonna take me around 5 months to get all the information from all the blocks. And if I do it with Alchemy and Infura every day, then obviously around 2 to 3 months. And the thing is that I thought it was a little bit strange, but in the first couple of thousand blocks I wasn't getting a lot of transactions. I was receiving empty lists of transactions. So I'm not sure what's going on there. I think this is happening because of the way that the internal functions and other stuff like that, the things I was searching about yesterday works, where I'm probably not receiving exactly all the transactions for each block, because otherwise I would expect that each block would have at least some transaction, otherwise there wouldn't be any purpose to have the block, I think. So yeah, but I think this is good enough for the stuff that I have access to, because even if I don't get all the transactions, I'm gonna have a bunch of different addresses, and then I can start playing around with this data and seeing what's possible. And then eventually further on down the line, I can start thinking about how different ways to get more information, probably using the Ethereum instrumental virtual machine or something like that, trying to dive deeper. But I think for now it's not worth it, probably. I think it's a better usage of my time, better use of my time to study the documentation here and to study the smart contracts from the DEXs, and then think about the logic on that. So I think now I'm gonna look this up here on the documentation, these methods here, and after I look at this, I'm probably gonna create a different file in the project and put on that file. I'm gonna look at the documentation for the decentralized exchanges, for the functions, the main functions, and I'm gonna write it down, the function and the implementation of the ones that I think are the most useful in a single file, so I can look that up later whenever I'm thinking about what I'm going to do with this. And should be fairly easy actually to, I think once, maybe in 5 days or something like that, I'm gonna have enough data. I think I already have enough data actually to build a PyVis Network X module visualization of the data frames that I have, which should be interesting as well. And then, of course, with these addresses that I'm getting, I will have to see what methods I can use in order to explore these addresses more, to see what I can do with these addresses. Which I think one of the things is get accounts, I think. To get all the accounts, then get balance probably. And I have to think about how I'm going to connect them, I think. That's the important part. What's the most relevant way to connect these addresses in order to see relationships between them? Because I think that's how it works. In social structures, you exchange information, and that's how relationships are formed. And those links of information follow physical principles, I think. So momentum and gravity and stuff like that. So I'm probably going to think about if there's a way to maybe code something along these lines of trying to find relationships based on this information. But then, yeah, the thing is I have to think more, because I have to see, yeah, that's probably the first step, is to see if I can get from the account addresses the transactions for specific addresses, and then I can make connections based on the transactions of each address. I think that's probably the best way. And with that, in the same way that I did with the script visualization stuff, where you can have a value for the size of the node depending on the amount of connections it has, I can do that with the same thing for the addresses, and then I can start seeing which addresses have more connections and how close together are some of their addresses. And through that, I think I can map relationships and start thinking about ways to predict patterns of behavior based on that, in the same way that you do in poker, where pretty much everyone gets used to doing things in a certain frequency, and by the average of probabilities, most people deviate towards the side of fear, which is folding most of the time. So you have to be aggressive, because that's how the limbic system works in relationship to risk and the unknown. And then 20% of the people are going to deviate more towards risk, and then depending on which profile you're playing against, you apply a different strategy. But then you can use data to map out and see what's more likely for each profile to be, and you can start mapping out more the environment, let's say, and understanding how the connections are made. But of course, this is just the idea in the surface. I'm sure I'm gonna find roadblocks along the way. It's probably not gonna be the way that I'm thinking in my mind right now. So yeah, so far I looked at this contract here. Oh, and these methods are from the Vue.js, not Vue.js, from the Web3.js. So they are going to be slightly different in the Python library. But I just realized that I could search for this on here. So I searched for the contract, and I think it just creates an object of a contract. And you pass the abstract binary interface and the address of the contract in order to create the object. So it's pretty simple. So now I have to look for these methods on this contract object. I think each contract is going to be different, that's the thing, because each contract contains different functions. So depending on the contract, I suspect you're going to be able to... I think the object creates a mapping, is like a class of the... Yeah, because each contract is a class. So when you create the class, this web3 if.contract, you're pretty much creating a class, an instance of a class. I think it works the same way. So each contract is gonna have access to different methods depending on what the contract is, I think. So that seems really intuitive to me. So I think I'm gonna put this on right away. Then if gets signers, I think this is to get... Yeah, I don't remember. Maybe the message.sender message value, but I think it's worth trying to figure out. I'm still searching. Yeah, but I like the... I think it's fairly simple, the idea that I have in mind of connecting addresses based on the transactions they have. Oh, and I made 2 different data frames. One is this one contain this one, and this one contain the initial stuff from Ethereum, which I later discovered that I was getting the information the wrong way because I wasn't transforming the hex. The information that I got, hex bytes, to a string, and in order to do that, use the .hex method. And because I wasn't doing that, then the rows got messed up in some of them. I don't really understand why, but then I figured out that I need to convert in order to get this string instead. And then I started a new data frame just so I didn't lose the other stuff, but and I didn't want to spend the time cleaning up the data. But I think it's not that relevant because it was just the first 80,000 blocks, around that. And out of 14 million is not that much. So hopefully with the Alchemy API they allow you to get more information at the same time. So this is taking a long time. I also have to study these libraries in Python here. I think that probably after I do the PyVis, I'm gonna have to implement some machine learning algorithms based on what I want to do, which is discover patterns in the data. And I think that's gonna be probably the hardest part to think about, because I know how to use the libraries to build simple AI models. I'm pretty sure I can look at the documentation as well, but I don't really believe the models that exist, let's say. I think they work, but they're very inefficient, and they're probably not getting... There's a bunch of hidden assumptions built on top of that, and that's the biggest challenge about this field, I think, is understanding the context of the data, which is always subjective, and what are the implications of that. And this impacts the way that you build the models, because you have to think about what exactly you think you are perceiving when you're getting all this data. The biggest problem that I can see right away is obviously the thing with the internal contract stuff, internal functions, and that I'm not gonna be able to capture all the addresses. So I have to be really careful with that. Yeah, so maybe if I search for something else, ethers, or maybe the Web3 library doesn't have, the Python library doesn't have this method. Contract factory, I think, is just getting the contract. Then Uniswap router, I think, is a function from Uniswap to make the swap of transactions, the swap of tokens. Artifacts, maybe this one is worth. Python artifacts. Yeah, it looks like I'm not gonna be able to search through that, I think. Oh, also, I didn't do this because honestly I didn't want to bother, but ideally I would put here a pickle file or something like that stores this information for the next loop. So once this breaks, the next time I start is gonna start from the last number where it broke. And here I'm just hard coding 80,000, so I have to be careful to not start from 80,000 again next time, otherwise I'm gonna repeat a bunch of information. So whenever it breaks, I have to remember to get this number and replace it here, so it starts again. And this here I've put because in some of the alchemy blocks it didn't have this true address. And I think so far, at least from first impressions, it seems like I'm able to get more information from the alchemy stuff than from the Infura one. And I'm not really sure if that's the case. But if it is the case, it's probably because they have access to different kinds of nodes, I think, or something like that. One thing that I'm gonna search that I don't know now are compile time. And this is just the initial stuff. Close this one. I just find the pain to code this abstract binary interface. It seems really redundant to me and annoying, so hopefully I don't have to do that. I think the main point of confusion I have regarding that is what exactly are people actually coding and what is coming from some compilation or parsing of some sort or some library. Whenever I was looking into the projects from before, it's kind of hard to distinguish the two. So let me go to the signers again. Entry, get signers. So maybe in the provider section I can find this. Oh, so this calls the functions in the contract. I think the get signers gets the accounts that deployed the contract. Maybe. This is interesting. I can, because I'm also retrieving the transaction hash from the call that I did there. So maybe I can use this method later on to get transactions from the addresses. Or maybe this is what I'm getting already, actually. Yeah, I'm getting this thing here. That's another thing. Maybe I'm getting the information the wrong way, because I just got this one from Stack. I don't think it was Stack Overflow, but some site thread. And then I did some modifications to create the data frame, but maybe not using the best method to get the stuff that I want. Yeah, this is the one that I'm using, so it's probably correct, actually. So what I'm looking for is get signers, or something similar to that. This is also interesting. The thing is, if you can do this stuff just Web3 with Web3, why would you even code a smart contract to do these transactions? I think probably the main benefit of actually deploying your own contract is the bundle transactions and the revert thing, where the transaction you don't get paid a fee, you don't get charged a fee if your transaction fails. That's probably why people use smart contracts. But it seems like it's not really necessary. And actually probably because if you're doing flash loans, you do have to get access to the other contracts as well. And I assume you can only do that with by deploying your own smart contract. And then the reason why people don't build a template, I think, general template that serves as a bridge between you and the other methods, is because it has to be specific to you every time, the contract, because you're gonna withdraw from the contract. So it doesn't make sense to create a template for everyone to use, or to find a template from another person. So this is the contract stuff. Sexual match. Yeah, I don't think I'm gonna find these get signers here. Maybe just with the Web3.js that exists. I know that they talked about it on the build space stuff. So maybe I should go back to that, it's probably easier. Should figure out. Let me see if I'm logged in. Now I don't know if this is the official site that I'm accessing or it's a phishing. Okay, I think I'm logged in. So let me go to the project. I think it's this one that they talk about, get signers. Maybe not. The only annoying part is gonna be to figure out which one. I think this is the one that I was looking at before. Oh, here it is, I think. In order to deploy something to the blockchain, we need to have a wallet address. Hardhat does this for us magically in the background. I grab the wallet address of the contract owner, and I also get a random wallet address and call it random person. So the first argument that it returns is the owner of the contract. But I still don't really understand that well, because and I don't think they're gonna explain. The first return is the deployer, the second is a random account. But they don't really explain how the method works. I'm just gonna search for hard hats, get signers, Web3, JS. Oh, so it's the in the window.ethereum. Hmm. So it's gonna be the address of the provider, I think. The first one. So either the provider is gonna be an endpoint like RPC, like Infura or Alchemy, or it's gonna be the window.ethereum, which is a wallet in the browser. Yeah. Signers. A signer in Ethers is an abstraction of an Ethereum account, which can be used to sign messages and transactions and send signed transactions to Ethereum network to execute state-changing operations. The available operations depend largely on the subclass used. For example, a signer from MetaMask can send transactions and sign messages, but cannot sign a transaction without broadcasting it. The most common signers you encounter are Wallet, which is a class which knows its private key and can execute any operation with it. JSON RPC signer, which is connected to a JSON RPC provider or subclass and is acquired using getSigner. I think I already read this stuff in the past, but it's good to remind myself of what it is. And there is a difference between this Ethers library, which I think I'm gonna put it save on the favorites, and the Web3 stuff. Contract Factory, I think I was reading something about this here somewhere. So actives are not intended to be initialized directly, instead create contract objects using the contract method. By default, the contract factory is contracts. See the example, concise contract for specifying an alternate factory. Contract provides a default interface for deploying and interacting with Ethereum smart contracts. The address parameter can be a hex or ENS name. I think I'm gonna search for what is that again, even though I think I already know what it is. Just to make sure. Each contract factory exposes the following properties: address, ABI, bytecode, functions, events. Okay, so let me read this here and then I'll move on to the factory. The signer class is abstract and cannot be directly instantiated. Instead, we use one of the concrete subclasses such as wallet, void, signer, and JSON RPC. Subclasses must implement this, however, they may simply throw an error. Returns a promise that resolves to the account address. The account address. This is a promise so that a signer can be designed around an asynchronous source, such as hardware wallets. Returns true if and only if object is a signer. Returns the balance of the wallet of this wallet. Returns the chain ID this wallet is connected to. Chain ID, I don't know what this is. Chain ID is introduced to prevent replay attacks between the main Ethereum and ETC chains, which both have a network ID of 1. It's basically just an additional way to tell chains apart. Subsequent to this thing, ETH has a chain ID of 1, while ETC has a chain ID of 61, even though they have the same network ID. It's required the network needed in every block or just the Genesis block. It's required for the chain to operate in general. It's required when signing transactions, meaning transactions signed on the Ethereum network end up with a different hash than those signed on OTC. So this brings me another question that I don't really understand that well. Genesis block. Genesis block is the name given to the first block, a cryptocurrency such as Bitcoin ever mined. The blockchain consists of a series of so-called blocks that are used. So probably the Genesis block is the root of all Merkle trees, branches. There's a unique header, and each such block is identified by its block header hash individually. These blocks get layered on one on top of the other, with the Genesis block being the foundation and the growing height until the end of the blockchain is reached and the sequence is complete. The layers and deep history of each sequence is one of the things that makes a blockchain-based cryptocurrency so secure. Bitcoin's Genesis block was the first instance of proof-of-work blockchain system and is the template for all other blocks in its blockchain. Blocks are effectively digital containers where data pertaining to the transactions on the network are permanently recorded. Block records some or all of the most recent Bitcoin transactions. Beginning with the fact that the name itself, yeah. Whatever. It's pretty much the first block. What is the limits of transactions per block in Ethereum? I wonder how the limit was decided as well, based on what was decided. It should be. I think I'm gonna keep going down the list to not get too sidetracked. Once I'm done with these ones, I'm gonna go back to this question here. This is probably good. To deploy a contract, additional information is needed that is not available on the contract object itself. Mainly the bytecode, more specifically the init code of a contract is required. The contract factory sends a special type of transaction, an init code transaction. I.e., the true field is null and the data field is the init code. So maybe that's why in some of this I wasn't getting the true in the transactions information is probably because they are contract factories, so they don't have the true address. Makes a lot of sense. Where the init code will be evaluated and the result becomes the new code to be deployed as a new contract. Any instances creates a new instance of a contract factory for the contract described by the interface bytecode. Consumes the output of the Solidity compiler, extracting the ABI and bytecode from it, allowing for the various formats the stock compiler has emitted over its file. What is the purpose of a contract factory? I think the purpose of a contract factory is to initiate different addresses, like a wallet does, but I'm not pretty sure. I can't really search here. Maybe if I search on YouTube, it's gonna be better. Even though I doubt that there's gonna be information about this. Maybe this one is good. And this one. It's probably the same block. So there's two different. That's why I was confused. There's two different contract factories. Yeah, so it's pretty much the Solidity's contract factory is pretty much a template, a contract that serves as a template to create other contracts, like a parent class. Not sure if it works the same way as is the same design pattern as an abstract class, or if it doesn't make that much sense to make that analogy. I think maybe not, because yeah, abstract classes, I think there are some methods that don't have implementation or something like that. I don't remember really well. And then Prometheus.js allows you to deploy arbitrary smart contracts to Ethereum network using our wallet. It means JSON, ABI, and bytecode usually get from Solidity compiler, along with a signer. So the contract factory from Ethers.js allows you to deploy contracts. To Ethereum using our wallets. Needs JSON API and bytecode. Solidity compiler. Ethereum from which enables deploying child smart contracts through parent smart contracts, Uniswap pairs. should just write it down here. So Uniswap, I think I'm gonna look at later. So I think I'm satisfied with this for now. I have to read these ones. Factory contract is used to create and deploy child contracts. Those child contracts can be referred to as assets which in the real life could represent, say, a house or a car. The factory is used for storing the child contracts addresses so that they can be extracted whenever necessary. Why wouldn't I just store them in my web app database, you might ask? By storing them in the contract, they remain in the blockchain and they are pretty much safe there. While data corruption in your database might wipe the asset contracts addresses, which will lead to losing references to those contracts. Also, you must keep track of all newly created contracts and update your database. Common use case for the factory contract is selling assets and keeping track of those assets, e.g. who is the owner. To sell an asset, you add the payable modifier to the functions responsible for deploying the assets. Here's the code. Check if there's enough to cover the car asset. The line address new car fires a transaction which deploys the child contract and returns the address for the contract. So it pretty much stores the addresses of other contracts created from that contract. The only connection between the factory contract and the assets is the variable address car assets. So make sure you store the addresses of the child contracts. Imagine you're building an app which has a dependency on multiple contracts, for example a blockchain copy of Amazon Store, which makes use of clothes factory contract, games factory contract, books factory contract, etc. Now imagine keeping all those addresses inside your app's code. What if those addresses change over time, or even more annoying, while developing you are deploying all those contracts every time you make changes and you have to keep track of their addresses. This is where name registry comes into play. This pattern allows you to only keep the address of one contract instead of tens, hundreds of, or even thousands. As your dApp grows in scale, it works by storing a mapping contract name, contract address, so each address can be looked up from within the dApp by calling getAddressClose factory. The benefits of storing names mapped to addresses is that with the introduction of new versions of some contracts, the dApp will not be affected in any way, since the only thing we modify is just the address of the mapping code. So this gives me the idea of getting these contract factories to retrieve all the addresses that are connected to them. So I think a good analogy is as if this is like the importlib library in Python, or pandas, or maybe importlib and numpy or something like that, where pretty much is the core of many of the scripts, if not all of the scripts. So they serve like as clusters of addresses, I think. So yeah. But I'm not sure if it is important to do that, because, or if it's gonna help in any way, because I still have to make as many requests to create the same amount of requests to the API to get these contract factories anyway. So I'm not sure if it makes any difference. But it might be useful to just make a pandas data frame with only contract factories. And the way I'm thinking about doing this is obviously with this if statement here, because if it doesn't have the true in the transaction, that means it's a contract factory probably. And then I can do, from that database, I can figure out a bunch of different addresses. And there's probably, these contract factories are probably going to be from dApps mostly, because probably most people are not creating contracts like this to store other addresses. That will be my guess, at least. The benefit of storing names mapped to address is that the introduction and new versions of some contracts, the app will not be affected in any way, since the only thing we modify is just the address of the mapping. Our app will use get contract details name to get the address and the version of the specified contract. Many times we need to iterate a mapping, but since mappings in Solidity cannot be iterated and they only store values, the mapping iterator pattern turns out to be extremely useful. Some things to keep in mind are that as elements count goes up, the complexity of the iteration will increase, as well as the storage costs, so avoid iterating when possible. Yeah, so that's the problem. It's probably not that efficient to do that. It's probably more efficient to do the way that I'm doing now, which is just get all the addresses and then I figure out how to get the transactions between them later. Common inputs could be iterating the keys to check for existence instead of doing it like this. Well, it's not exactly an error, it is not desirable since iteration becomes costly as keys already goes. So if draw pattern. Okay, so I think I'm gonna close this one. I'll close this one for now. How to be the contract factory that creates contract clones. The following article was written by Upstate Interactives. Last year we began working on a DAO for commercial client comprised of 9 smart contracts. We can't get into the specifics per NDA, but in summary, the DAO enables its collective of users and shareholders. A key feature. The code. I think it's probably gonna be redundant at this point. Let's look at this. Alright. Contract factors are extremely useful because they support use cases wherein it is desirable to clone exact contract functionality with a minimum of side effects, e.g. memory slots stomping, and with low gas cost deployment of duplicate proxies. This is extremely powerful in distributed systems where you want the end user to have access to an implementation contracts functionality, all while still maintaining full control over their own contracts storage and state. Their standard contract factory architecture looks like this. So the factory, proxies, logic contract. The factory contract itself is used to generate identical proxy contract clones that forward transactions through and from the implementation contract which contains the logic. The factory can often also be used to update the implementation contract's address so that new proxy contracts will have new upgraded functionality. Furthermore, you can customize factory controls and add admin privileges such as updating the implementation contract. Uniswap, the Ethereum-based protocol designed to facilitate automatic digital assets exchange between Ethereum and ERC20 tokens, uses a factory contract. to create exchanges contracts for any ERC20 token that does not already have one. It also functions as a registry of ERC20 tokens that have been added to the system and the exchange with which they are associated. Low-friction wallet solutions like Ethereum uses a factory to generate user wallets, or proxies that the end user themselves own and use to access their favorite apps in any mobile or native app. Context loans for the different entities and organizations. Contract factories can be used to empower end users and provide them with ownership and control over their own proxies, storage, and state. Contract factories are also very useful when it comes to generating upgradable proxy contracts. Lastly, contract factories used in conjunction with proxy pattern architectures are quite common. We therefore encourage developers to utilize the EIP 1167 standard on OpenZeppelin's proxy factory base contract. Yeah, I see this OpenZeppelin stuff a lot as well, so it's probably important to study that. Yes, let me move on to these artifacts. I think get account is pretty self-explanatory, so get balance as well. Block header, retrieve. I don't think I'm gonna look at this. Also, yeah, this Winstone, might have to look at it because I don't know what it is. The other ones I'm not gonna look at it. Maybe I'll look into it later. Artifacts, Ethereum, Ethers, Web3, Jazz. And the thing is, I don't remember where I saw this. So I don't think I'm gonna search for this now. Probably gonna. If it is important, it will show up. I'll look into it later. Let's see, Winstone. Web3, there's. I think I'll bread back. Maybe I'll change the music. So it seems like Winstone is a logging library. The way to use Winstone is to create your own logger, simplest way. I don't think I'm gonna spend a lot of time watching this, understanding this one. Oh, this is the object that I get from the block request, and this is what I use to create a data frame. Each thing on red is a column, and this is the object that I receive for the transactions list. And I decided not to do a data frame for the uncle blocks. And they also come in a list, so I couldn't put in the block one. And uncle blocks are pretty much the blocks that are not yet the ones that are kind of like branches. In the same way that Git has branches, the uncle blocks are the branches, and the main tree are the blocks, the official blocks, as far as I understand. And then eventually all the uncle blocks, if they get enough transactions, they become the main one. They merge into the main one, I think. So now I think I'm gonna start studying these ones for Union Swap. V3 documentation. And this stuff I'll leave for later, after I study all the documentation from the libraries, and I have the data, and it's time to do analysis, then I'll look into this. Let's see. Oh, I'm gonna finish reading these ones first. I think I can close this one. I think I'm gonna close this as well. If a block acts as a ledger of transactions, how many transactions can fit in a block? I should set up private testnet where only one machine is allowed to mine while others are performing transactions on its blockchain. The following is a simplified explanation of what GIF does. There are two main places where transactions can be, in a block or in the transaction pool. When a node first hears about a transaction, it puts it in the transaction pool. These are essentially zero confirmation transactions. There's a number of ways to access this, most particularly depending pseudo block in Web3. When a node starts to mine, it will take the highest paying transactions in the transaction pool, one by one, and execute them. When it runs out of the gas limit or transactions in the pool, it commits to the mining that specific block. This appears in the console as something like commit new work on block X with Y transaction. It then continues hashing that block until it finds a hash that is sufficiently rare enough for the block to be accepted by the network. Every other transaction, whether it was received before it started work on the block, but could not use it for some reason, or whether it received afterwards remains in the transaction pool until it's mined, or becomes permanently invalid for some other reason. And it still doesn't answer how many transactions exist on each block. Depends on the maximum block size. What maximum block size in Ethereum? Just refer this link. Okay. I think I saw on the documentation at some point something talking about this. It has a maximum and a minimum size depending on the network, on the transactions, the volume that is going on. No maximum Ethereum block size, while Bitcoin has a fixed block size of 1 MB, Ethereum's block size varies. Instead of a fixed limit, Ethereum block size is bound by how many units of gas can be spent per block. This limit is known as the block gas limit, sometimes confused with transaction gas limit. At the time of writing this, miners are currently accepting blocks with an average block gas limit of around 10 million gas. Currently, the average Ethereum block size is anywhere between 20 to 30 KB in size. Ethereum miners determine what the maximum gas limit should be by signaling it to the network each block. Miners are given the ability to adjust this rate because changes to the gas limit affects the resources necessary to effectively mine Ethereum. So that's an interesting thing to know as well. I guess this is one point of manipulation that can happen. Or miners having control of the block size. How many Ethereum transactions fit into a block? It depends on how much gas each transaction spends. The answer to this question varies because not every transaction is the same size. For example, the base cost of any transaction is 21,000 units of gas. However, transactions that are more complex or require more storage on the blockchain will cost you more gas. Generally, the more operations a transaction executes, the more it will cost in gas. Theoretically, someone could spend all of a block's gas limit in one transaction. How does an adjustable block size affect network performance? The biggest benefit of an adjustable block size is that the Ethereum blockchain chooses how it wants to scale. Users and developers determine the demand for gas, and miners are able to choose what gas limit or block size is viable to their operations. When the Ethereum network is experiencing full blocks, it has the option to raise the gas limit. However, it's worth noting storing data on the blockchain is costly, and there comes a point where their two options are the preferable scaling solution. Raising the gas limit has the potential to increase the average block size, ultimately affecting the cost of nodes on the Ethereum network. Larger block sizes means that the space required to store the Ethereum blockchain grows faster. Bigger blocks and the possibility of less nodes on the network can affect Ethereum's uncle rate. These are all factors taken into consideration when the Ethereum community choices whether to support changing Ethereum's gas limit. I really enjoyed this article. So they also have an API. I guess that's one idea to make money as well, is run a node and then create an API and then sell data. It doesn't seem like it's that difficult to do. The only initial requirement is to have enough money to hire a server. Then you could probably set up a node quite easily. Run on a server. And then obviously the cost of marketing as well. To get people to buy subscription. When the Ethereum network begins to feel a bit congested, it's not uncommon to see terms like gas limit and uncle rate thrown around. They appear in discussions centered around raising Ethereum's block gas limit per block, not to be confused with the gas limit set when sending a transaction. This limit restricts the total gas which can be spent by the transactions contained within each block. Miners collectively have the ability to increase or decrease Ethereum's block gas limit within a certain range. The question I have is how they do that as well. Because if they're not, how are they agreeing to a limit? It's also something I still don't understand. And theoretically, raising the limit enables the Ethereum network to process more transactions per second. Maybe asking yourself, why don't miners just keep cracking up the gas limit? That's where the uncle rate comes in. Ethereum's uncle rate, or rather the rate at which uncle blocks occur, plays a big role in the discussion whether the gas limit can or should be adjusted. In order to understand the importance of the uncle rate, let's define what an uncle block is. Each block in the blockchain is farmed from the one before it, also known as its parent block. When multiple blocks are produced from the same parent, only one becomes part of the blockchain permanently. The other block produced but not included is known as a stale block. Due to Ethereum's shorter block times, stale blocks can occur more often. And so Ethereum is designed to reward miners for producing blocks even if they don't quite make it into the chain. So I guess when you're producing a block and it doesn't get into the chain, you wouldn't make any money from mining the transactions because they're not valid. So that's why this reward exists. Stale blocks can be included into the chain as an uncle block or Omer block, the gender neutral term. To the chain as an uncle block. An uncle block is defined as a child of a parent of a block that is not the parent. God damn. Child of a parent of a block that is not the parent. Oh, okay, I got it now. So it divides in just one level below, outside of the tree. So it's the stale block that has a child block, and that's the uncle block. Block produced from the grandparents of the current block that is not the current block's parent. Ethereum rewards miners with a small block reward for producing uncle blocks in an effort to combat centralization. Uncle block rewards might make mining on lesser hardware or mining outside of the largest mining pools more cost effective. Uncle block rewards make mining on lesser hardware or mining outside of the largest mining pools more cost effective. Why does Ethereum's uncle rate matter? Say the miners choose to increasing Ethereum's gas limit. A higher gas limit means more transactions per block. More transactions means more data, which means larger block sizes and a larger blockchain state, which needs to be stored by miners and nodes. Overall, a higher gas limit means it costs more resources to run a node. This can reduce the total number of nodes on the Ethereum network. Furthermore, potentially less nodes and larger blocks can affect how fast blocks spread throughout the network. Stale blocks occur more often if nodes spread blocks slower than they are produced by large mining pools. More often if nodes spread blocks slower than they are produced by large mining pools, leading to a higher rate of uncle blocks. See if I understand this part. So they occur more often if nodes spread blocks slower than they are produced by large mining pools. So pretty much large mining pools are producing more blocks than the nodes, which are the separate miners, leading to a higher rate of uncle blocks. Because the mining pools are mining faster than the other nodes will create more uncles. I think I get it now. All these factors combined gives the Ethereum community a sense of how well the network is handling the load we're putting on it. If the uncle rate is low and the congestion is high, it might be time to consider increasing the gas limit. If the uncle rate is skyrocketing and nodes are falling off the network, the gas limit may be too high, affecting the security of the network. Although recent research into faster block propagation technology may change things, routing blocks through the Ethereum network faster could allow for larger blocks without higher uncle rates. So this brings me to the question of how are miners deciding the block size, the gas limits of block size. Because how do they agree on what's gonna be the block size? I guess it's because I don't really understand how the fee for mining is set up, how the reward they are getting is set up. It's probably based on the computation, but I don't really understand that well. I think I have to understand this before I even go through the Uniswap stuff. It's better to understand more how the mining works. I think here, oh no, it's still running. Yeah, so it looks like, oh no, when it reaches 160,000 then I'm gonna see if it's more than 100,000 requests a day that I have. Close this. think I already read this one. Ethereum mining layout explanation. Each transaction has a gas limit. For example, there could be 5 on-mine transactions where each has a gas limit. The block gas limit determines how many transactions can fit in a block. If the class... Every person who creates a transaction can decide what their transaction's gas limit is, but it would not make sense for them to specify something higher than the block gas limit. So, GIF and other clients would prevent them from setting too high. It is a gas limit because it is the maximum amount of gas the person creating the transaction is willing to use. They do not pay for any extra gas that is not used. But if they set the limit too low, their transaction can run out of gas and they pay for all of it to the miner. With the block gas limit, miners are the ones who decide. The bigger it is, the more they can get from transaction fees. With the more bandwidth and computing they would have to do. Miners cannot change the block gas limit too much within one block. They can only change it by a factor of 1 to the 124. The transaction gas limit is the gas property in a transaction object. Transaction gas limits. So I guess this one here. Gas used. Gas limit here. Oh, here, gas. These numbers are not correct. I erased a lot of them just so it was using less space and easier to read. The block gas limit is a parameter in the Genesis file created. It is client dependent and typically means the minimum block gas limit. A block with a gas limit smaller than it will not be accepted by the nodes on that blockchain. So I guess this is one of the flags that you can use when you're setting up a GIF as a miner to determine how much you're gonna pay for gas, and then people choose different settings depending on their setup. Because I doubt on average probabilities people are selfish, so they're gonna do what's best for them, and the mining pools are probably gonna choose higher gas fees because they want to make more money, and the other nodes are gonna choose the lower gas fees because they don't have that much computing power. And then it's gonna create a situation where it's gonna fluctuate, and depending on how much it fluctuates, it creates more or less uncle nodes, uncle branches, uncle blocks. And then more uncle blocks is bad because it starts becoming centralized, because most of the mining is being done by mining pools, and then you have all these nodes with uncle transactions that stop being rewarded because they're not being connected to the main block. So there's always the balance, but I still don't understand really well what makes, because if that's the case, then it wouldn't have any difference. People would just choose the best for their specific reason, and then the limit wouldn't change. It would only change based on who is mining, how who is mining is changing over time. But maybe there's other factors, other incentives for people to change the gas as well. Not just how much they're gonna make, but other factors like different transactions and stuff like that. But it feels to me like I'm missing something, because it can't be. No, there is this heuristics that determine the minimum and the maximum from the Genesis block, I think. But outside of that, there must be something that dictates from time to time if it's gonna go up or gonna go down, kind of like inflation, where you have the government lowering or increasing interest rates depending on the situation in order to balance the flow of money. So I assume there's probably something like that in the chain as well. Otherwise, it would probably fail long term based on the probabilities, because the momentum is probably for mining pools to take over the more power the chain, the network has, and trying to control more of the stuff, which creates a Pareto distribution, because that's how market economy incentives shift over time. So there must be, unless they calculated that and made so the probability, the rewards would balance themselves out. So the reward for Uncle blocks increases. Yeah, that's probably the way that they did it actually. So as the Uncle blocks go up, it starts diminishing the rewards for big mining pools and start increasing the rewards for the Uncle blocks, and then it balances out. I think that's what they did probably. But it seems like it's probably an impossible thing to actually code, because the future is unpredictable, so it's not. I don't think it's possible to figure out an equation that's gonna work for every situation to balance out the limits. So I think I still need to read more stuff about this to fully understand. So maybe how were gas limits set up in Ethereum. But I feel like this is gonna be the simple explanation. Let's say Alice had to pay Bob if the transaction gas limit is 21,000 units and the gas price is 20 GU. Total fee would have been gas limit times gas price unit. When Alice sent the money, would be deducted from Alice's account. Bob would be credited on if. Miner would receive 0.042. Offers a concise overview of gas. And let's watch this.
Gas? To run your car, you need fuel. To run an application on Ethereum, you need gas. The gas mechanism makes Ethereum extremely efficient at allowing scarce resources on the network. Everything on the Ethereum network costs a little bit of gas, including transactions. Gas on Ethereum has a market price determined by demand for resources on the network. The amount of gas you need depends on how large of a contract you're trying to execute and how fast you want to execute it. If you are willing to wait longer, you can pay less gas. If you want your contract or transaction executed faster, you pay more gas. Many functional tokens today have taken efficiency ideas from the Ethereum gas market and applied them to problems in other industries. Many believe the future lies in this kind of very efficient use of decentralized resources, which benefits all participants.
And this is just the basic stuff. The Londo upgrade was implemented on 20 to make transactions on Ethereum more predictable for users by overhauling Ethereum's transaction fee mechanism. The high-level benefits introduced by this change includes better transaction fee estimation, generally quicker transaction inclusion and offsetting the issuance by burning a percentage of transaction fees. Starting with the London network upgrade, every block has a base fee. The minimum price per unit of gas for inclusion in this block, calculated by the network based on demand for block space. Calculating the network based on demand for block space. So it's the supply and demand thing that I was talking about. As the base fee of the transaction fee is burned, users are also expected to set a tip priority fee in their transactions. The tip compensates miners for executing and propagating user transactions in blocks and is expected to be set automatically by most wallets. Calculating the total transaction fee works as follows. So gas units limit times base fee plus tip. So I think I'm gonna write this down here below this stuff. Is equal gas units limit times base fee plus tip. Let's say Jordan has to pay Taylor 1 ETH. In the transaction, the gas limit is 21,000 units and the base fee is 100. Jordan includes a tip of 10 Q. Using the formula above, okay. Additionally, Jordan can also set a max fee for the transaction. The difference between a max fee and the actual fee is refunded to Jordan. Jordan can set a maximum amount to pay for the transaction to execute and not worry about overpaying beyond the base fee when the transaction is executed. For the London upgrade, Ethereum had fixed sized blocks. In times of high network demand, these blocks operated at total capacity. As a result, users often had to wait for high demand to get included in the block, which led to a poor user experience. The London upgrade introduced variable size blocks to Ethereum. Each block has a target size of 15 million gas, but the size of blocks will increase or decrease in accordance with network demand, up until the block limit of 30 million gas to access the target. I think I read this part. That's why I was thinking that there is a low one. I remember reading this thing here. The protocol achieves an equilibrium block size of 15 million on average through the process of tautomnus. I don't know what this is. This means if the block size is greater than the target block size, the protocol will increase the base fee for the following block. Similarly, the protocol will decrease the base fee if the block size is less than the target block size. The amount by which the base fee is adjusted is proportional to how far the current block size is from the target. That's very, very interesting and really, really intelligent, actually. Blocks are batches of transactions with a hash of the previous block in the chain. This links blocks together in the chain because hashes are cryptographically derived from the block data. This prevents fraud because when a change in any block in history would invalidate all the following blocks, as all subsequent hashes would change and everyone running the blockchain would notice. To ensure that all participants, how blocks work. This is the more basic stuff. This is the London thing. Every block has a base fee which acts as a reserve price. To be eligible for inclusion in the block, the offered price per gas must at least equal the base fee. The base fee is calculated independently of the current block and is instead determined by the blocks before it, making transaction fees more predictable for users. When the block is mined, the base fee is burned. The base fee is calculated by a formula that compares the size of the previous block, the amount of gas used for all the transactions, with the target size. The base fee will increase by a maximum of 12.5% per block if the target block size is exceeded. This exponential growth makes it economically non-viable for block size to remain high indefinitely. Yeah, this is what I thought as well. The stuff I was saying about the uncle blocks. So they pretty much put it into a formula to find the equilibrium of the changes in supply and demand to balance the network based on the gas limit, so that the people will naturally set up their gas limit based on the how congestion the network is. But I'm curious on how do they come up with the formula. Because it also seems that it is impossible to find the true equilibrium, because there are multiple players, so yeah. So I guess that's another interesting thing to look at based on the block information that I'm getting, which is try to visualize or try to derive the formula based on the amount of transactions per block or the gas limit for each block, which I have here. So I think an interesting thing, that sounds very interesting, to make analysis based on the gas limit and the amount of transactions at each point in time, and see how they fluctuate over time. Just see the rates of information and how that affects behavior. But it seems really that will be really difficult to do, so I'm not sure if I'm gonna do that. But the reason why this is very interesting to me is because of something I was thinking about in the past, that is that the thing about the limbic system overfitting the environment through the lens of market economy. So pretty much the tendency for the Pareto distribution based on the normal probabilistic distributions that make up the personality profiles of social structures, which becomes the fractal Pareto distribution of the hierarchies of competence that creates the flow, the money, which is basically the market economy is a decentralized computation that creates these hierarchies on different domains in order to adapt in relationship to the environment. And here I think that's pretty much the way they are thinking about this as well, which is that the gas limit is what determines this fluctuation of the markets. If I understand this correctly. So it's like inflation as well, where you have this balance, kind of like a wave between, depending on supply and demand. And then what matters in that is understanding the frequency of that wave to see how it's going to change the structure of the social structure overall across time, because that determines the innovation and the adaptation of people in relationship to the environment. It's a closed feedback loop system. So I think understanding that might give me insights on how to create a system that might be better to implement, that is more, say, anti-fragile, in relationship to these fluctuations. But I'm not really sure. I have to think a lot more about that. Just to see if it makes sense. Yeah, I have to think about what kind of information is possible to about human behavior is possible to get from these shifts in gas limit and how it affects the network itself. I think what I'm trying to understand is what are the factors, the principles behind the fluctuation. I think that's what's important. So, in other words, what stimulus in the environment incentivizes shifts on the structure of the network, of the supply and demand, which is probably gonna have a lot to do with the limbic system. But then that's the problem, because it gets really complex, because then you have to put social media as well, information about social media, because it's probably based on narratives and how the information is spread over time. I think that's the key point. And then it becomes much more difficult, because you have to get data from a lot more places in order to do this type of analysis. But I think it might be a good start to think about these things using this gas limit stuff. So I think I stopped here. Relative to the pre-London gas auction market, this transaction fee mechanism causes fee prediction to be more reliable. Following the table above to create a transaction on block number 9, on what will let the user know with certainty that the maximum base fee to be added to the block is current base fee times. Yeah, that's another thing. The miners only decide the maximum and minimum, I think, because there's also this fee that the user can choose, which is also gonna affect the limits, I think. Maybe it doesn't affect the limit actually. It just affects the size of the block based on the limits. It is also important to note it is unlikely we will see extended spikes of full blocks because of the speed at which the base fee increases preceding a full block. For the London upgrade, miners would receive the total gas fee from any transaction included in the block. With the new base fee getting burned, the London upgrade introduced a priority fee tip to incentivize miners to include a transaction in the block. Without tips, miners would find it economically viable to mine empty blocks, as they would receive the same block reward. Under normal conditions, a small tip provides miners a minimum incentive to include a transaction. For transactions that need to get preferentially executed ahead of other transactions in the same block, higher tip will be necessary to attempt to outbid competing transactions. And that's where the PGA of bots comes in, which is another interesting thing to think about, is how are these bots affecting the behavior of the system as well. Which I assume, based on just first principles, that what's happening is polarizing more, because that's what power does, and technology is power. So it just polarizes the structure more, which increases the frequency of change in the wave that makes up the whole fractal normal probabilistic converging to fractal Pareto distribution probabilities. So it's just increasing the frequency of the cycle, I think. It's like faster innovation that creates different impulses that shape the innovation and just polarizes more as a byproduct of that. Yeah, but the only potential solution is probably changing the incentives, the structure itself of the way that markets work. But I'm not even really sure if that would balance the growth with the regulation. Yeah, I have to think a lot more about that actually. To execute a transaction, the network users can specify a maximum limit they are willing to pay for the transaction to be executed. The optional parameter is known as the max fee per gas. Calculating fees, one of the main benefits of the upgrade is improving the user's experience when setting transaction fees. The implementation, the loan transaction fees. So let me search for gas auction. So maybe I'm also not understanding really well how it works. And this doesn't have a lot of things. Maybe in the official documentation I can find information about that. Users can submit transactions with a max fee per gas corresponding to how much they are willing to pay for the transaction to be executing, knowing that they will not pay more than the market price for gas. In short, gas fees help keep the Ethereum network secure by requiring a fee for every computation executed on the network. We prevent bad actors from spamming the network in order to avoid accidental or hostile infinite loops or other computational wastage in code. Each transaction is required to set a limit to how many computational steps of code execution you can use. The fundamental unit of computation is gas. Although a transaction includes a limit, any gas not used in a transaction is returned to the user. Gas limits refer to the maximum amount of gas you're willing to consume on a transaction. More complicated transactions involve smart contract. Why can gas fees get so high? High gas fees are due to popularity of Ethereum. Performing any operation on Ethereum requires consuming gas, and gas space is limited per block. Yeah, and I guess all this stuff is also going to change with the proof of stake thing as well. It's probably a whole different model on how it works. I have to study more about that as well. Fees include calculations, storing or manipulating data, or transferring tokens, consuming different amounts of gas units, I'm curious to see. I think, yeah, I'm gonna try to understand how this whole calculation of the inflation and deflation is gonna happen on proof of stake, because now I think I understand how they thought about these fluctuations when it comes to mining, to miners. But I think probably the same concepts will apply, but I think instead of mining fees is gonna be based on the staking amount, something like that. As that functionality grows more complex, the number of operations, yeah, but then the issue, if it is on the staking amount, becomes the problem of the centralization and stuff. So there's probably a balance there as well, somehow. The number of operations a smart contract performs also grows, meaning each transaction takes up more space of a limited size block. If there's too much demand, users must offer a high tip amount to try out and outbid other users' transactions. Higher tip can make it more likely that your transaction will get into the next block. Gas price alone does not actually determine how much we have to pay for a particular transaction. If you have to... Initiatives, okay. Have to multiply the gas used by the transaction fee, which is the equation here. Initiatives to reduce gas costs. The Ethereum scalability upgrades should ultimately address some of the gas fees issues, which will in turn enable the platform to process thousands of transactions per second and scale globally. Layer 2 scaling is primarily an initiative to greatly improve gas costs. The new proof-of-stake model introduced on the Beacon chain should reduce high power consumption and reliance on specialized hardware. This chain will allow the decentralized Ethereum network to agree and keep the network secure, while limiting energy consumption. Anyone with at least 32 ETH can stake them and become a validator responsible for processing transactions, validating blocks, and proposing new blocks to add to the chain. Users who have less than 32 ETH can join staking pools. Yeah, so it pretty much becomes a lot more centralized. That's the calculation. Yeah, $86,000 minimum in order to stake. At least with the Ethereum prices today, or close to the Ethereum prices. I'm not really sure if, but it's probably around that range. If you're looking to reduce gas costs for your ETH, so maybe what I should read now is gas limits on Ethereum proof of stake, or maybe this one as well. Yeah, I'm gonna read this one before. Understanding the problems. Okay, to add each block to the chain, miners must compete to solve a difficult puzzle using their computer processing power. To add malicious block, you'd have to have a computer more powerful than 51% of the network. The first miner to solve the puzzle is given a reward for the work. There's no competition as the block creator is chosen by an algorithm based on the user's stake. Yeah, so I think it's pretty much by luck that the algorithm works. In order to add a malicious block, you'd have to own 51% of all the cryptocurrency on the network. Yeah, that one is already a little bit suspicious. There's no reward for making a block, so the block creator takes a transaction fee. Trying to think about how does this work here. How the validation process works to become a validator. Why Ethereum wants to use proof of stake? The Ethereum community and its creator are planning to do a hard fork. Blah, blah. It will be implemented. There will exist validator pool. Users can join this pool to be selected as the forger. This process will be available through a function of calling the Casper contract and sending Ether or the coin who powers the Ethereum network together with it. There is no priority scheme for getting inducted into the validator pool itself. Anyone can join in any rounds they want, irrespective of the number of other joiners. The reward of each validator will be somewhere around 2 to 15%, but it's not sure. Safe for any computer. System validators do not have to use their computing power because the only factors that influence their chances are the total number of their own coins and the current complexity of the network. So this possible future switch from the two may provide the following benefits: interest saving, safer network. This way, Casper will be a security deposit protocol that relies on an economic consensus system. You must pay a security deposit in order to be part of the consensus thanks to the new block's creation. That doesn't explain much. How validators work here. It's another mechanism that activates validators upon receipt of enough stake. Ethereum users will need to stake their tree to become a validator. Validators are chosen at random to create blocks and are responsible for checking and confirming blocks they don't create. A user's stake is also used as a way to incentivize good validator behavior. User can lose a portion of their stake for things like going offline, failing to validate, or their entire stake for deliberate collusion. But how is this programmed? I wanna know. How does the actual algorithm works? So maybe if I search for a proof of stake algorithm, it's probably better. When Ethereum replaces proof of work with proof of stake, there will be added complexity of shard chains. These are separate blockchains that will need validators to process transactions and create new blocks. The plan is to have 64 shard chains, with each having a shared understanding of the state of the network. As the coordination is necessary and will be done by the beacon chain. Also, splitting a database horizontally to spread the load. Beacon chain receives state information from shards and makes it available for other shards, allowing the network to stay in sync. Beacon chain will also manage the validators from registering their stake deposits to reaching their reward and penalties. When you submit a transaction on a shard, a validator will be responsible for adding your transaction to a shard block. Validators are algorithmically chosen by the Beacon chain to propose new blocks. If a validator isn't chosen to propose a new shard block, they will have to attest to another validator's proposal and confirm that everything looks as it should. It's the attestation that is recorded in the Beacon chain rather than the transaction itself. At least 128 validators are required to attest to each shard block. This is known as a committee. The committee has a time frame in which to propose and validate a shard block. This is known as a slot. Only one valid block is created per slot, and there are 32 slots in an epoch. After each epoch, the committee is disbanded and reformed with different random participants. This helps keep shards safe from committees of bad actors. Once a new shard block proposal has enough attestations, a crosslink is created which confirms that the inclusion of the block in your transaction in the Beacon chain. Once there's a crosslink, the validators will propose the block gets their reward. In distributed networks, the transaction has finality when it's part of a block that can change. Slow. The threat of 51% attack still exists in Proof of Stake, but it's even more risky for the attackers. Stake ETH, not only is this a lot of money, but it would probably cause ETH value to drop. It's very little incentive to destroy the value of a currency you have a majority staking. There are stronger incentives to keep the network secure and healthy. I'm not sure if I completely agree with that. I think it depends on the context. A lot, actually. War being the main example. I thought this can go very bad. Stake slashings, ejections, and other penalties coordinated by the Beacon chain will exist to prevent other acts of bad behavior. The thing is, I'm not sure how much money that would be, but I guess, yeah, because that's the thing. How are you going to verify that? I get that's the weird thing about it, because I don't know how it works really well. Because if you have access to, you can just print a bunch of money and pretty much buy 51% if you want to. So I have to understand more how that works. It's still something that is kind of difficult for me to understand. The connection between the normal, let's say, money and the blockchain money. How does the bridge works? I guess it is based on the rules that are created. Yeah, but it still leaves space for exploiting, because yeah, what would happen if someone printed a lot of money and just used that printed money to buy a bunch of Ethereum? And that's the thing, how would they do that? That's the question that I don't know. Because you always have to buy from someone else, and you have to... Yeah, maybe the wallet creation part of the thing, that I have to study more to understand this. How are wallets first created, and how does the deposit works when they are first created? Staking makes it easier for you to run a node. It doesn't require huge investments in hardware or energy, and if you don't have enough ETH to stake, you can join staking pools. It allows for increased participation in more nodes, doesn't mean increased percentage returns. So I guess my main question now is this thing about the wallet. How people I guess you just create out of thin air and then people decide to trade money for it. That's how it works in the beginning. There still needs to be a bridge there between real money, not real money, but normal money, and the token. And it works in the same way that different currencies work as well, but I'm just trying to think more about it, just see. It's the same logic, but it's a different way based on the technology, of course. I guess it always involves politics at the end because of the regulations, and it's just the flow of energy through different rule sets, I think. The interesting part for me to think about is how the rule sets are created through this flow of energy. Because of the question that I had before of the inflation, of what if someone decides to print a bunch of money and put it, but then that's gonna have a lot of effects as well. That's the thing. It's gonna have macroeconomic effects on the currency of the country and the lending and borrowing, which is gonna affect everything else. But it is a possibility, nonetheless. But I guess we just have to work with probabilities, which makes sense. Yeah, but the main thing for me that I'm interested about is trying to put the metrics on what determines the physical relationship between these things. So, what is the probabilities of the move the flow of energy through these systems? The Bitcoin chain doesn't change anything about the Ethereum we use today. It will coordinate the network, same as the consensus layer. Bitcoin chain will conduct or coordinate the expanded network of shards and stakers, but it won't be like the Ethereum mainnet of today. It can't handle accounts or smart contracts. So it's similar to the principle of an uncle, but it doesn't handle accounts and smart contracts.
Centric roadmap view, what changes in ETH2 phase 2? So do we even need state execution across these 64 shards? We have sharding in this data availability layer and we're scaling with rollups. Does ETH2 phase 2 get a lot more simple?
Because chain's role will change over time, but it's a foundational component. The Beacon chain will introduce proof of stake for Ethereum. This is a new way for you to help keep Ethereum secure. Think of it like a public good that will make Ethereum healthier and earn you more ETH in the process. Staking and becoming a validator is easier than mining, and it's hoped this will make Ethereum more secure. If you're interested in becoming a validator and helping learn more about staking, so maybe I should read this as well. I wonder if anyone has put metrics on network effects of how big I guess it's pretty much the same way that mass works. I think it's pretty much the same thing, where the more mass you have, the bigger the momentum and inertia, and the flow of money is the flow of energy, which becomes mass. So it's just a flow of information. The initial momentum is where the transition happens, where some people take the leap of faith and go from the standard to the new thing, until the new thing picks up mass, and then it becomes the new norm. And then it becomes part of the balance of the overall thing. So it becomes another currency, which is a trading pair with all the other currencies. And then the probability that someone will deposit 51% is also relative to all the other probabilities that all the other currencies are under, which depends on politics and the macroeconomic incentives of different companies, depending on the structure of the technology around the planet at the moment in time, I think. It's the same thing with this that I have with computers. I think I understand how it works, but it's still hard to wrap my mind around the fact that it actually works, where you have something out of nowhere and then it just becomes a thing because everyone believes in it. Like the moment of transition is very, very interesting, because that's what essentially you have to create systems around, to try to measure and not based on definite outcomes, of course, because you can't predict the future, but based on probabilities, so that you can try to build systems to regulate the potential of innovation, so that it doesn't become destructive before you're fast enough to regulate after the fact that the damage is already done. That's why I think it's interesting to me. There's also nothing saying how long you should stay. You have to validate for. But I guess people probably made videos about this already, so I'm gonna watch those later, probably. After mainnet merges with the Bitcoin chain. So I think I'll stop studying this for now. I'm gonna move on to the Uniswap stuff. So I think my mind's a lot more clear, except the gas limit stuff, because now I think it's gonna change based on this proof of stake. It's gonna be, the block size is probably gonna be determined based on the fees instead of the gas limit, because the validation is gonna happen randomly. Yeah, maybe there are not a lot of explanations yet, because I think the change didn't happen, hasn't happened yet. So I think I'm gonna study Uniswap now. Right back. I think it might be a good place to stop here actually and cut out so I can study Uniswap in another video. Yeah, I'm gonna stop here and I'm probably gonna come back later today to start studying Uniswap. I don't think if there's anything else that I'm thinking about now when it comes to Ethereum. So I think I can close this one. Yeah, this is still running. Yeah, I'm gonna spend all my time studying these libraries until I have enough information, I think, on the data frames to start thinking about actually doing things with them. Another thing that I have to think about is how the proof of stake is gonna change this gathering of information. Because obviously now the blocks are gonna be different. But I think probably it's gonna be the same way, it's just gonna be different information that you get for different blocks. But like it said there in one of the articles that the transactions won't be on the blocks, the validators won't have access to that or something like that. The sharding nodes won't have access to the addresses and the transactions, and that might be a problem based on what I want to do in order to know the addresses. But then I assume there probably will be different ways of getting the addresses to the validators or something like that. So let's see. Yeah, so I think I'm gonna stop here, and then when I come back, I'm gonna start studying this Uniswap stuff. So see ya.